All right, guys. So in this video, I will be making some presentation on metric space topology, and as well, we'll be reviewing some important examples on metric. Now, as we all know that metric simply means distance. So we have that. Let x to be a non-empty set. Of course, we are dealing with a non-empty set. So a function that is the distance mapping s to x is said to be a metric, or is said to be a distance function on x if the distance d satisfies the following conditions. So the first condition is that dx comma y must be greater than 0 for every value of x and y in x. Second condition, dx comma y equals 0, that is if x equals to y. Third condition, if xy equals to yz, yx. So this is called the symmetric property. The last one, which is called the triangle inequality, we have it to be dx comma z less than equals to dx comma y plus dy comma z for every value of x, y, z in x. So when we bring the function itself with the distance together, then we call it what? A metric space. But it is just an ordinary metric if it is x alone. But once we bring the distance and the function itself together, it becomes a metric space. So we have a question, and unbounded, we have that the distance of x comma y equals to the absolute value of x minus y on R. So we have to show that D is metric on R. So we are following the different axioms that we have, that is x minus y greater than 0. Now since dx comma y, since the absolute value of y of x minus y is greater than 0, definitely their distance must be greater than 0. The second condition, since the absolute value of x minus y equals 0, this implies that x equals to y, and for this reason dsy comma y must also be 0. Condition 3, that's the symmetric property. When you have x minus y, of course it is included in an absolute boundary, so it is possible that we have y minus x, and the absolute value of y minus x will give us the distance of y minus x for all x, y in x. And lastly, for the triangle inequality, we can split our x minus y to be x minus y plus y minus z, so it still remain constant. So when you introduce the less than equality sign, so we can split the absolute value into two parts. So we have our final answer to be dxy plus dyz. So example 2, we have sd to be a metric space, and we have the function to be equals to xy over 1 plus dx. So the first condition, the second condition, and the third condition is satisfied. Similarly for the first one, similarly to the first one. So let me quickly explain the condition 4. The condition 4, which is the triangle inequality for the second question, is that we have dx xz. So we have to look for a way to manipulate xz. So we can write xz to be xy plus yz. So recalling from the equation, everything becomes xz over 1 plus xz, since we are dealing with x comma z now. So when we have that, but the inequality we are using is that if a is less than b, it is already proved that a over 1 minus 1 plus a is less than b over 1 plus b. So this is the condition surrounding this principle for this very question. So this is the condition we are using. 1 over a over 1 plus a is less than b over 1 plus b. So that's the condition we are using. So as a result of this, we split the inequality into two parts. So we have that dx comma y over 1 plus dx comma y plus 1 plus dy comma z, similarly to the other part. So you can see now that we can intentionally remove one of the one of the parameters. That is, for the first one we remove y comma z, and for the second one we remove x comma y. So the reason why we have to do this was because a less than b is same as a over 1 plus a less than b over what? 1 plus b. So condition 4 is satisfied. Now connectedness, when we talk about connectedness, if we have a metric space, a metric space is said to be connected if the only set that are open and closed are both open and closed in X. Sorry, that are open and closed is X and file itself, that is, it is X and empty. So when we have an empty set and we have the set itself, so we say that the set is said to be connected. So we have to show that the absolute value of xn comma yn minus dx comma y less than xn comma x plus dyn comma y. So proving this, what we should focus on is we focus on the parameters. We focus on dx dyn comma y, and we focus on dxn comma x. So we apply symmetric property to those two parts. After applying symmetric property to those two parts, we multiply everything by a negative sign, and when we multiply by a negative sign, the sign changes. So the sign changes, the symbol changes to the other part. And recalling that minus m greater than equals to minus p and less than equals to p is the same thing as the absolute value of m less than equals to p. So that's what we apply there, and we have our equation proven. So that's very straightforward. You can as well check that out. So isometry, when we talk about isometry, we have two metric spaces. We have xd and yd to be two metric spaces. So when we have a map x to y, it's called an isometry if and only if f preserve the metric, that is, the distance of fx1 comma fx2 is equals to the distance of everything in brackets for every value of x1, x2, and x. When we talk about contraction also deals with two metric spaces, and we have a mapping tx to y, and we must have a constant ranges from 0 to 1 such that the distance of the first one is less than equals to the constant multiplied. So the difference between isometry and contraction is that for contraction we have a less than equals to sign, and we have a constant c multiplying the distance all together. So Banach's contraction principle. So from the definition of contraction, we already know that tx map to y, but in this case we are mapping tx to x. So it is a contraction if t has a unique fixed point. So the unique fixed point is that x is mapped to s, it is not mapped to any other values, so it is mapped to x. So the point x in s is such that tx is what is equals to x. So completeness, when a metric space is complete, it is said to be complete if every Cauchy sequence in S is convergent in X. So you should know about Cauchy sequence in real analysis. We also have Cauchy sequence in metric space. So it is said to be complete if every Cauchy sequence in X is convergent in X. All right. Mind you, we can all convergent sequence is not necessarily Cauchy. So when we talk about Cauchy sequence, the Cauchy sequence, when you take the distance of two different function xm comma xn, it must be less than what? It must be less than epsilon. So that's what Cauchy sequence is. That is, a sequence in a metric space is said to be Cauchy if for any epsilon greater than 0 there exists natural number in n such that whenever m is greater than n and n greater than n, we have their distance to be less than epsilon. And for convergent sequence is a sequence in a metric space is a function xn. Of course, if we are dealing with a sequence in metric space, we have xn or x in bracket n. So if it converges to x in x, then we have that xn is in bx comma it has an open ball. So we have that for convergent sequence. Now for compact, a subset k subset x of a metric space is said to be compact if every open cover of k admits a finite subcover. So that's compact. Then we have another example here. We have that let f a comma b map to a b be differentiable, and the absolute value of f prime of x is less than equals to c. So we have to prove that f is a contraction on ab. So recall from mean value theorem from real analysis, we can use mean value theorem to prove for this, and using mean value theorem respectively, you see that it obeys contraction. So if you go back to the definition of contraction here, you can see that contraction is less than equals to constant times the distance. So that's what we have here. Now, um we have let x, d, and y, d to be two metric spaces. We have to show that dx1 s2 comma y2 is defined as the maximum value of dx1 s2 dy1 y2 respectively. So there's nothing difficult. What you do is we apply all the necessary axioms for a metric space. So all the axioms, axiom 1 is satisfied, axiom 2 satisfied, axiom 3 satisfied, and lastly the triangle inequality, which is axiom 4, is what is satisfied. So it is well explanatory. You can just go over it and check that. Then lastly, we have to show that a convergent sequence in a metric space is bounded. Yes, a convergent sequence in a metric space is bounded, but the otherwise is not necessarily true. That is, a bounded sequence in a metric space is not necessarily convergent. An example for that is when you have minus 1 raised to power n in R. So that is a bounded sequence that is not convergent. Do you understand? But in this case, we have that a convergent sequence in a metric space is bounded. So we have to prove this. So let x to be a metric space and Sn be a convergent sequence. You know, we already discussed this, that Xn is a convergent sequence. So if we map Xn to X and we let epsilon to be equal to 1, because we are told that for every epsilon greater than 0, so it is mandatory for us to equate epsilon to a number greater than 0. So we are equating it to be 1. So when we take the distance of xn comma xn, it is less than 1 for every value of n greater than equals to n. So we let another m to be the maximum distance of x1 x, s2 x. Now if this keeps on going, you will see that it moves up to xn minus 1 comma x, and the last point should be 1, because we already said that epsilon to be equals to what? 1. So if we are considering the distance itself from triangle inequality, for us to split the distance of sn comma xm, we have that it is xn comma x plus x comma sm, and from the above we have that to be m plus m, which is 2m. So it means that the sequence sn is what is bounded. So these are the few examples we will do in this video. So as time goes on, I'll release some other videos on metric space topology, and we'll check out some principles. So you can as well go over the examples that we've made, look over for them, and understand very well. Thank you.